All right, welcome everyone to this lecture. What we're going to do today is to start talking about the Aldol reaction. And so the Aldol reaction is kind of a fun reaction because it takes two carbonyls and reacts them together, using one of them as the nucleophile and the other as the electrophile. And so what that really means is that we must be using an enol or enolate as a nucleophile and a different carbonyl as the electrophile. And I will show those in two different colors here. For the aldol reaction, we'll either use a ketone or an aldehyde, not an ester or anything else for the electrophile. The enol or enolate can be of any carbonyl containing functional group. But again, the electrophile needs to be a ketone or an aldehyde. So overall in this reaction, we have, again, a nucleophilic enol or enolate, so nucleophilic carbon-carbon pi bond. And that pi bond will attack the carbon of the carbonyl. Overall, after some proton transfers, so I'm not showing details here, but overall, again, getting you to now what is called a beta hydroxy ketone. In case it helps a little, I'll go ahead and label where the electrophilic atom is, where it's ending up, and also where the nucleophilic atoms are and where they might be ending up in the product. So once you have this beta hydroxy ketone here, turns out that can undergo an elimination reaction as well. So this is kind of set up nicely here. And so you actually have two different steps to an aldol reaction. There's first an addition to the carbonyl, getting you to the beta hydroxy ketone. After that, depending on the reaction conditions, you can either do an E1 or an E1CB process to get to the eliminated product, which is now an enone, so a conjugated ketone. And this is formally called the aldol condensation product, while the initial kind of intermediate of addition is just called an aldol addition product. And so a big question that comes up in doing aldols is, well, how do you know where to stop? Do you stop at the alcohol or do you go all the way to the elimination? Turns out this is a tricky question to answer. Generally speaking, the higher the temperature you are, the more condensation and elimination you'll get, so that should feel familiar from our last unit. And then it turns out that if you're using acidic versus basic conditions, you get different results. So under acidic conditions, you're a little bit more likely to do the E1. So most acid catalyzed aldols will end in a condensation. And for basic conditions, it'll really depend on your reaction conditions in terms of after the initial aldol addition, is there enough energy in the reaction, or is there enough equivalence of base left to do the E1CB reaction? So we'll start off with a simple case, and that's the self-aldol reaction. So that's when a carbonyl molecule is reacting with itself. And so that looks like an enol or enolate form of the carbonyl reacting with another molecule. And so we'll do the very simple example of acetone. And so if you take acetone and do an aldol condensation, this is the product that you get right here. This reaction can take place with either catalytic acid or base. And that reflects the fact that you can do it with either an enol or an enolate nucleophile. And so we'll look at both of those mechanisms, starting with the acidic one. And so remembering that under acidic conditions, we can have this keto-enol tautomerization. That means that some fraction of our ketone will be in equilibrium with an enol. And so that's definitely the first step that's required. We need to generate the nucleophile that will be used in the aldol reaction. The electrophile now is a second molecule of acetone. And since we're under acidic conditions, we'll want to protonate it. So I'm just showing the protonation step here because we'll need an more electrophilic electrophile to react with this less nucleophilic enol. The attack looks just like an attack on a carbonyl, addition to carbonyl. And what we want to kind of keep track of here is that the initial carbonyl is reformed. So the carbonyl in black here is remade in this first aldol addition step. And again, I'm kind of labeling the electrophilic site just to help you a little bit. After a proton transfer, if our overall goal is to do the condensation reaction, we can transfer the proton from the carbonyl over to the alcohol. And this actually makes sense in terms of pKa's because we're going from a lower to a higher pKa. And so this is actually a very favorable reaction, and this is part of why the elimination of water from the aldol addition product is favorable under acidic conditions. And so I'm drawing here the leaving group leaving, so the first step of an E1 reaction, then the second step where the water that had left can come back and deprotonate. And this deprotonate should be fairly favorable because you end up making a conjugated carbonyl here. And then finally in the reaction, we do regenerate the acid, and so that makes this catalytic in acid. All right, so now we'll do the basic mechanism. Very similar, just a base instead of an acid. I'm going to use hydroxide as our theoretical base, but it could be any other sort of base. And in the first step of this mechanism, we should expect to be forming the enolate instead of an enol because we're under basic conditions. The equilibrium still should favor the keto form here, not the enolate, based on pKa's. But as soon as any enolate is formed, that is nucleophilic, and it would be possible for that enolate to then react with the electrophilic carbonyl. In this case, now we have a stronger nucleophile, so enolate stronger than enol. So the weaker electrophile of a non-protonated carbonyl is reactive enough. We can do our carbonyl addition, getting us to that beta substituted carbonyl. In this case, a deprotonated oxygen. So from here, then what we need to do to get back to the beta hydroxy carbonyl is to protonate it. And so what we can then use is the molecule of water that we had made before and do our deprotonation. That gets us to the beta hydroxy carbonyl. And so at this stage, we've completed the aldol addition part of the aldol reaction. And so if you're thinking about this acid-base step right here, we should be able to recognize that the pKa of water should be relatively similar to the pKa of an alcohol. From here, what we need to do is an elimination step. And because we are under basic conditions and we have the potential for a stabilized carbanion here, what we do is a deprotonation first and then the elimination second. So that's this E1CB mechanism that we saw in the last unit. So again, deprotonation getting us to this carbanion, which might take a little bit of time before it actually does the elimination. And after that's all said and done, we'll get to the same product. So again, a conjugated carbonyl, in addition to reforming our catalytic base. Okay, so now that we've looked at self-aldols, I think we should move on and look at aldols between two different carbonyl-containing compounds. This is a little bit more valuable and interesting because if we're trying to build up molecules with increasing complexity, then you are likely to be using two different types of carbonyl-containing compounds. So in this example here, I have benzaldehyde and acetophenone. And so I'm reacting these together with tosic acid, so strong acid. And if we're looking at the two molecules here, there's actually only one set of hydrogens that can be used to make an enol. And so that means that the acetophenone here must be the enol, the benzaldehyde must be the electrophile. So I've gone ahead and labeled the electrophilic atom here. And so if we're drawing our product, we can start off with our nucleophile, and then draw on our new bond, and then the electrophilic carbon, and then fill in the rest of the blanks there. This is a good place for you to check if you understand the mechanism well, so I'll let you go ahead and try that. Just make sure you start off making an enol from the ketone. All right, here's another example. So again, a crossed aldol reaction, so that means a different nucleophile and a different electrophile. In this case, I'm giving you a parahydroxy acetophenone and a kind of a metafluorobenzaldehyde here. And so again, we have the situation where there's only one site where we can even make an enol or an enolate. And so that's definitely the nucleophile on the left, electrophile on the right here. I'm going to give you basic conditions just so that we have something different to look at. And under these basic conditions, we should be able to predict what the product looks like. So if we are doing an aldol condensation, we can draw our nucleophile, fill in the double bond, figure out where our electrophilic atom is, plug that in at the other end of the double bond, and then fill in the rest of the groups that are attached to all the atoms. And so as you're looking at this reaction, you might notice something a little bit strange, which is that we actually have a very acidic proton right here. right? Because that's a phenol, and we should be used to seeing phenols getting deprotonated by all sorts of bases. So a very legitimate question is, well, why doesn't the acid-base reaction from potassium hydroxide here just take place with the phenol and kind of get us stuck, or do a different type of reaction? And well, we can look at our pKa's just to make sure. Phenol pKa is about 10. The pKa of a ketone is about 20, so definitely very, very different. And then the pKa of the conjugate acid of the base is water, which is 16. So definitely we should be deprotonating phenol. And so what we can think about is what reaction would even happen if we did that. And so let's try to do that. So phenoxide here attacking any carbonyl. There's a bunch of different carbonyls you can attack in the reaction. What you would get is the formation of a tetrahedral intermediate with the carbonyl oxygen being negatively charged and then the phenol here. But then that would just collapse back down. So yes, you would deprotonate phenol. That would be a nucleophile to attack a carbonyl. The problem is you would make a tetrahedral intermediate that could collapse and go back to the original starting material. And so what's happening there is that even though the majority of the time we have deprotonated phenol and that's the nucleophile, that doesn't really accomplish anything. That's all just in one big equilibrium. And the tiny percentage of the time that we deprotonate the ketone instead, causing it to do an aldol reaction, that kind of ends up going toward product, and this is the thermodynamic sink overall, because there's no going backwards once you've made this double bond here. And so an important thing to recognize in these reactions, and the self-aldol reactions I showed you on the previous slide, is that these are all being done under equilibrating conditions. And what that means is that the enol or enolate, so in this case the enol that I'm pointing at under acidic conditions, is actually kind of a minority presence in the reaction. Most of the time we're in the keto form. The acid catalyzes the formation of a little bit of enol. That little bit of enol is in equilibrium, but eventually can do an aldol reaction. Same thing in the second example. Our ketone is the weakest acid amongst the bunch here. And so most of the time in our acid-base reaction, we are in the ketone protonated form here. We're going to have potassium hydroxide. The little bit of the time that the base successfully deprotonates to make an enolate, that enolate can continue reacting to get us to a product. So we don't really care about all these other possibilities like deprotonating out here because those are non-productive. And our equilibrium allows us to reach overall what's the most stable product. Of course, all the examples I've given you so far have been kind of nice, successful aldol reactions, and nothing bad can really happen. But there are many challenges in doing these types of crossed aldols between two different carbonyl-containing compounds. And so one example is here. So let's say I take this diterbutyl ketone here, and I want to do an aldol reaction with acetaldehyde, hoping that my aldehyde is going to be the nucleophile and the ketone is going to be the electrophile. Well, if I do that reaction, what I'll find is that actually this ketone is way too sterically hindered. It's not going to be a good electrophile at all. And so actually, as soon as I make any enol or enolate of the aldehyde, it will react with a second molecule as the electrophile. And so what I won't get is the intended condensation product here, again, because it's not the best electrophile in the reaction. And instead, I will get the self-aldol reaction between two aldehydes, because aldehydes are so much more electrophilic. You might ask, well, aren't we under equilibrating conditions? Can't we get back to this product in the end? Well, the reason we can is because once you get to the condensation product, you're in a stable sink and you can't get out of there. So once you make this, you're stuck. Okay, here's another example of a challenge. So let's say I take acetone and I want to react it now with 2-butanone and I want to do an aldol reaction. Well, now there's not really a great choice in terms of where my enol or enolate is going to form. And so what that means is that I have multiple different potential aldol products because both of my molecules are equally good at being nucleophilic or electrophilic. And so that means that crossed aldols will only really work well if we are correctly using the most electrophilic carbonyl as our electrophile and the most easily enolizable carbonyl as our enol. That all being said, this is only true if we're thinking about equilibrating conditions. And you've already seen this in alkylations and halogenations, but there's ways to preform an enolate or an enol. and use that in your reaction. So that's what we'll look at next.